Hello, everyone, and welcome to TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. We've got another great interview for you this time around, but first, a quick update on the drawing we've been running in conjunction with O'Reilly Media. As you know, if you've listened previously, O'Reilly Media is holding their first ever AI conference on Monday and Tuesday, September 26th and 27th in New York City. The conference will span both low-level talks on implementing AI and high-level talks on the impact of AI in society, and I'm personally looking forward to speeches by AI luminaries such as Google's Peter Norvig, Facebook's Jan LeCun, and Intel/Nirvana's Naveen Rao. And we're giving away a ticket to one lucky winner here today. In addition, right after the AI conference on Wednesday and Thursday, the 28th and 29th, is the O'Reilly Strata plus Hadoop World Big Data Conference, which is one that I've been attending for years now. You may have heard me mention this one before. Strata is a much bigger event, and while it's not strictly focused on AI, there are tons of really interesting AI and machine learning talks at Strata as well, along with talks focusing on what I consider to be the core topics of that event, data infrastructure and data engineering. And O'Reilly has been kind enough to offer us a ticket to Strata as well, which we'll be giving away today. So, about that giveaway. If you went ahead and entered into the contest via either Twitter or the TWIMLAI.com website before the cutoff date, your name or Twitter ID went into a spreadsheet and you actually had a pretty good chance of winning as far as giveaways go. I chose winners using a random number generator to pick 4 numbers in the range of my spreadsheet rows. The first winner, who was lucky number 17, is Lance Poole, who entered via Twitter. Lance gets to choose either conference ticket for his prize. The second prize winner is Yinka, also from Twitter, and he gets the ticket remaining after Lance's choice. I've also chosen 2 runner-ups who may be called upon to fulfill the duties of one of our winners if either of them can attend the event. Our first runner-up is Samuel W., and our second runner-up is Dennis A., who both happen to have entered via the TWIMLAI.com site. If you hear this, any of you, please reach out to me to claim your prize. Now, if you didn't win, it's not too late to save 20% on your registration for either conference. You can do that by using the registration code PCTWIML when registering, and I'll include a link to the registration page in the show notes. On behalf of the podcast and our partner O'Reilly, thank you to everyone who entered. And now, on to the show. All right, folks, I am super excited to bring you this interview. My guest this time is Charles Isbell Jr., professor and senior associate dean in the College of Computing at Georgia Institute of Technology. Charles and I go back a bit, and in fact, he's the first AI researcher I ever met. His research focus is what he calls interactive artificial intelligence, a discipline of AI specifically focused on the interactions between AIs and humans. Charles and I spent a good chunk of time in our interview exploring what this means and some of the interesting research results in this field. One part of the discussion I found particularly interesting was the intersection between his AI research and the related fields of marketing and behavioral economics. Beyond his research, Charles is well known in the ML and AI worlds for his popular machine learning course on Udacity, which he teaches with Brown University professor Michael Littman. In addition, Charles helped launch the Online Masters of Computer Science program at Georgia Tech. We spend quite a bit of time talking about what's really missing in machine learning education and how to make it more accessible. Of course, I'll be linking to Charles and the resources we mentioned in the show notes, which you'll be able to find at twimlai.com/talk/4. And now, on to the interview. All right, everyone. So I'm here with Charles Isbell. Charles is Senior Associate Dean and Professor at Georgia Tech. And actually, Charles and I go way back. So This has been a weird conversation because we're already like 20 minutes in and just getting started with the interview. Charles, say what's up to everyone, and we'll get started.
What's up, everyone? How are you doing? I'm happy to be here and happy to be having this conversation.
Awesome. Well, thank you so much for joining us for this interview. Now, I think we figured out that it's been like 20-something years since we met, and that was pretty interesting in that we were roommates during I guess, summer internships at Bell Labs. And that was when you were at MIT and studying AI. Tell us a little about your experience at MIT and what you studied. You're in the famous AI lab there, right?
I was, although the AI lab no longer exists. It merged with the Laboratory for Computer Science and is now known as CSAIL. So I loved my time at MIT, and I loved my time at Bell Labs and eventually, AT&T Labs. Sort of my journey through AI is it's a bit of a wandering one. So here, I'll just give you my entire history up to now in like 15 seconds, and we'll see how that goes. So as you can tell by my accent, I was born in Chattanooga, Tennessee. But my earliest memory is arriving in a moving truck at the age of 3.5 in Atlanta. So I think of myself as being from Atlanta. From very, very early on, I cared a lot about computers and computer science. And I knew when I was 8 years old that I was going to do computer science, although I didn't know what it was. I knew I was going to be a professor, although I didn't know what it was. And I knew I was going to do AI, even though I had no idea what that was. Something about building robots. At 8 years old. It took me a very long time to realize that not everybody thought they knew what they wanted to do when they were 8 years old. I think I was probably a senior in college before I realized this. But I'd always sort of wanted to build intelligent things, although I couldn't have articulated it that way when I was 8 years old. But I always wanted to build smart things. I thought the computers were great, or at least what I thought computers were. And I basically just wanted to build, an intelligent friend. That's basically what I was into at the time. And so everything I kind of did from at that point on was about that. My actual first encounter with Bell Labs, long before we met, I think it was the summer before 9th grade, so I was 13 years old or so. And I built a computer at Bell Labs as a part of this summer science program. When I say I built a computer, I mean there was a kit and another engineer did all of the work while I stood there and watched him. But it felt like I was building the thing. It was a Timex Sinclair T1000. And
I think I have one of those.
Yeah, it was a little chiclet thing, and it didn't have an on-off switch, so when you turned it off, you had to unplug it. It was great. And the first program I ever wrote was a piece of code that would fill up the screen with inverse spaces, and it ran out of memory before it could finish doing it. And that was my introduction to real computers. So, that's I figured I needed to fix that. And so that whole summer we spent, the 2 or so weeks that I was there for that program, I spent a lot of time trying to figure out how to make computers smart and how to make them do what you wanted to do. And it just verified for me that that's what I wanted to do for all of my life. So I kind of dove in from there, and I kept getting bigger and better computers and convincing my mom that an Apple 2GS was the right thing and it was the best thing she could do for my education. She kind of nodded politely and eventually gave me the things that I wanted, and I sort of moved through. And one of the advantages of knowing what you want to do with your life is that you sort of move towards it. There's some disadvantages. We can talk about those, but really it meant that I knew I wanted to go to Georgia Tech because I wanted to stay in Atlanta, and I thought that it was the best place for me to be. So I went to Georgia Tech as an undergrad. I completely dove into AI. Didn't do a lot of research at the time because that, in the 1980s, it was there weren't as many places where you could do the kind of research that you can do now as an undergrad, no matter sort of what you're into. And then decided, there was basically one place for me to go to grad school, and I applied to MIT, and I went to MIT. And I wrote this long essay about building robots and trying to make them smart and trying to make certain that they wouldn't run out of memory. And it was a lot of fun. So I ended up going to MIT, immediately started diving into machine learning, which at the time was sort of new for me. I knew about AI and I knew I wanted to build robots, but it didn't occur to me that you needed to do something separate to make machines learn. And I decided almost immediately once I was exposed to it that this was the central question. You couldn't be smart unless you could learn. Right. And our machines were never going to be able to do the interesting things that I wanted them to do when I was 8, 9 years old, unless they were smart enough to learn how to do them on their own. And so I dove into that, became a part of the AI lab, went through a couple of advisors. I'm still good friends with all of them, and eventually ended up where I was. The side story where we met is at the same time that I was going through grad school, I got to go to Bell Labs every summer. So part of this fellowship program, you know all about this, of course. And there I did a lot of really interesting things in AI that had absolutely nothing to do with what I was doing in grad school. Mm-hmm. But it was so interesting what they were doing. They were trying to build these knowledge representations and kind of really understand how it is you could think and you could represent thought, that I just, at the time it felt okay that I wasn't making progress in grad school because I was still getting to do these cool things. And so by the time we met, I was doing 6 months out of the year at Bell Labs and 6 months out of the year at MIT, more or less.
Oh, wow. I don't think I realized that at the time.
Yeah, because I take 4.5 months over the summer. I'd start before everyone else and I would end after everyone else, and I would go back during the winter breaks.
Okay. So I think the time that you kind of came up in AI was during the quote unquote AI winter. Is that right?
More or less. We were just sort of at the tail end of the AI winter. Nobody told me that. I didn't figure that out until much later.
So how has that impacted your and your contemporaries' perspective on AI and the work you've done? And what do you think about the current popularity of AI and where it's all going?
I think basically what it's mainly done is the people who are about my age and a little bit older who lived through the AI winter, I think basically spend a lot of their time wondering when the next AI winter is going to come. So a lot of us are very, very sort of naturally and reflexively worried that we're overhyping what's going on, right? It wasn't that it was difficult to get funding. It wasn't that it was difficult to do work. It wasn't that there weren't people interested in the problem that we were interested in. It's that any minute now, the federal government would take away all of the funding, and we would go from having 10 graduate students to having 2 graduate students. And I kind of think that little fear is always there in the back of our heads, and we find ourselves thinking, please stop overhyping deep neural networks, or getting people convinced that we're gonna build the next data or the next Android and self-driving cars, and at any minute it can all kind of go wrong. So I think it's probably made us somewhat more cautious, or at least it's made me somewhat more cautious in trying to think a little bit about the hype. That's sort of where it's kind of driven me. But the other advantage of being a part of sort of AI when it was during the AI winter is that you knew that you and the people you were talking to were in it because you were truly passionate and motivated about solving the problem, as opposed to starting a company that would make you really rich, or this is the hot thing. You were doing it because you actually cared about it, and I think that that's important, right? Certainly when you're doing research, you have to be passionate about the things that you're doing and really believe that somehow it's going to get you someplace interesting.
And so, do you think? Fear notwithstanding, do you feel like is the industry structured in the same way such that the risk is the same, or is it different? And in particular, I'm thinking about, is there, are the funding sources more distributed now? Is the level of industrial activity, more greater now? Or is it all, from a research perspective, all still fundamentally the government funding everything, and when they decide to when the winds change there, it all collapses?
Well, I think structurally, 2 things have happened. One is computing, and that sort of way of crunching things, and data are now ubiquitous. They're everywhere. So industry is deeply into this. It's not going away. Google exists, right? And everything is driven by data. And it turns out that the parts of AI, the parts of computer vision, all the sort of pieces of building intelligent things, they're driven by data now. And since everyone has access to data, and everyone has access to computing, everyone has access to really fast machines, I'm not worried about sort of it structurally going away. In fact, the problem is sort of the opposite. It's that everyone has a piece of it now. It's driven as much by commercial interest as it is by sort of pure research. And so really the difficult thing in some ways is that there's so many opportunities to do what I would have thought of as AI, what we would talk about as machine learning and those kinds of related things, that it's easy for things to become diffuse. In a way that wasn't true 25 years ago. I don't think this is a bad thing. I mean, the fact that Facebook exists, the fact that Google exists, the fact that everything is about data and about sort of modeling what people are doing and what things are happening is definitely a good thing. And it does mean that there's always going to be funding for some piece of it, even if it's not being called AI or it's not being called machine learning. The kind of idea is metastasized. So I'm not really worried about it going away. The only thing that worries me is that people are concerned that bad things will happen because of what we're doing. And for good reasons, right? They're concerned about their privacy. We now have all this ability to track everything that you do. I guarantee you, Google is well aware that you and I are having this conversation right now. They probably know what we're going to say before we say it. They've got more data on us than you can possibly imagine. And truthfully, I'm not entirely sure that we mind. Facebook knows everything about us. There are companies out there neither of us have heard of who know kind of everything about us. So people are worried about privacy. They're also worried about cars running off the road and killing other people. They're worried about robots, rising up in Terminator style, killing us all. So the kind of fear is the hype has actually gotten to the point of not, well, you haven't given us what we promised. It's that you've given us more than what we asked for. I think that's where the danger is coming from now. But in terms of funding, in terms of people being interested in these problems, no, that's driving everything, even things you don't think of as being AI or being machine learning.
Mm-hmm. Yeah, it's interesting that in some ways the industry is given more. In some ways, like we're still waiting. Like if you survey sci-fi and even the Jetsons, where sci-fi thought we would be in 2016. In a lot of ways, we're not there yet, right? Like a lot of movies would have had the self-driving cars all over the street. But some of this stuff, it takes longer. It takes longer to develop than you think, and some of the stuff is happening quicker than you think.
No, I think, and some of the things are happening that nobody ever thought about. I mean, you go back and you start thinking about sci-fi. It wasn't self-driving cars; it's self-driving jetpacks, right? I still haven't gotten my jetpack yet. I'm still waiting for that. And it's true. We haven't gotten the flying machines. We haven't gotten the smart butlers that are taking us everywhere. On the other hand, we've gotten a lot of other things, right? We've got access to information that we've never had access to before. We can ask questions and we'll get the answers back. We can look up anything we want to. We can teach ourselves. We've gotten a lot more of things we never thought about than we thought we would. And we've gotten less of the kind of obvious things that I think people sort of hoped that we would one day get. So, it's a mix. I'm okay with that. I mean, people ask me all the time, when are the computers going to achieve sentience and take over the world? And I think the answer is probably never, or at least probably not for a very, very long time. Not in the way that people think about it, but we're going to have very smart machines, and we already do, doing a whole lot of things for us that we never sort of expected them to do. And the interesting thing is we won't even notice, and it won't seem like that big of a deal. I mean, for example, with the Tesla and the autonomous cars, Uber, and all the things that they're doing, that's amazing. Have you ever been in one of these cars?
Yes.
Have you ever led through this? That's amazing that you can sit in that car and it can drive you through traffic on a highway at 65 miles an hour. That's amazing. If you had asked me how you would do something like that 25 years ago, I'd be like, I can barely figure out how human beings do it. And in fact, being on the road, it's pretty clear to me lots of human beings don't do a very good job of it. But that's a miracle, and we barely notice, right? Every time you get in an airplane, right, the pilot's not flying, the airplane's flying itself.
Right.
And we just take this everyday miracle as just another little thing. In fact, one of the big complaints, if you're into AI, right, is that you never actually get credit for the cool things that you do, right? AI is kind of the science and the engineering of making computers act the way they do in the movies.
Right.
But one of the things that's sort of tied into that is if it's got to be intelligent, then it's got to be like humans. And if it's got to be like humans, it has to be mysterious and something we can't understand. So the problem is every time we do something, even if it's amazing, once we know how to do it and we understand it, well, that can't be real intelligence. And so we don't give the credit to AI. So AI sort of has this problem where you can't ever win because anything interesting you do, well, we understand that, and that's not real intelligence, so it's no longer AI.
That's just machine learning.
Yeah, or it's just computers, right? It's never this thing where you've succeeded. It's just oh, that's not the real part. The real intelligent part is this thing. And then when you can suddenly beat people at Jeopardy, well, that's not really intelligence. The real intelligence is this other thing. So you basically just keep innovating your way out of business. And so AI gets sort of smaller and smaller and smaller in what it's allowed to call itself, because the mystery gets smaller and smaller.
Is it smaller, or further?
Well, it's always sort of infinitely far away, right? Right. It's something that we can always look for, but we can never quite get to. Sort of Zeno's paradox of AI.
But there's not like there's not some finite set of things that we need to do to figure out AI, and we're chipping away at it and it's getting smaller and smaller. It's like the goalpost is moving.
Yeah, well, so I think both of those things are true.
Or both?
No, I think that's accurate. I think both of those things are true. I think there are a finite number of things we need to do. We're definitely chipping away at it. And so the stuff we need to do sort of gets smaller and smaller, though it's still really big. But the goalposts keep moving, right? We've got cars that can drive themselves, more or less, and now that's no longer amazing. So it's got to be something else. But that's amazing. And by the way, it's not just amazing. It has an amazing impact on the world. Have you seen this? I know you're on Facebook. So you remember this map that was going around for a while that showed the most common jobs in every state? Do you remember this? It's floating around about a year or so ago.
Yep.
And do you remember what the most common job is in almost every state in the U.S.?
Truck driver, right?
Yeah, truck driver, delivery person, taxi driver. Right? That's something like 42 or 44. I don't remember the right number, but it's over 40. For some reason, in other states, it's elementary school teacher. I don't know why, but mostly it's truck driver. Well, we're 5 years away from all the cars driving themselves.
Right.
Right. Uber is not going to have people involved anymore. My old advisor, one of my PhD advisors, is heading the work at Prime Air. Right. Mm-hmm. So things are going to be delivered to us by drones, and people aren't going to be involved anymore. Well, that's the most common job in the country, and it's going away, right? So the goalposts are moving. The things we have to do are getting smaller or not, and people have this sort of feeling what AI is. But whether or not you want to call it AI or not, it's going to have a massive impact on our day-to-day lives. It's going to have a massive impact on the economy. It's going to have a massive impact on sort of how we see ourselves and how we interact with one another. And whether you decide that it's AI or not, or it's intelligent or not, and whether you move the goalposts or not, it's changing everything around us in deep and profound ways.
Yeah, absolutely. So I want to talk about a couple of really specific things with you, and we'll take these in turn. The first is in the realm of education, and the second is in the realm of your research focus area and reinforcement learning. But let's start with the first of those. We got through your grad school experience at MIT, then you went back to Georgia Tech. And most recently, you've been doing a lot of work in online education around machine learning. Maybe walk us through what you're doing there. And in particular, I'm curious, and maybe as a bit of background here, I didn't go through your entire course, but I took a look at the course that you did with Michael Littman, and I really enjoyed the presentation. Having gone through a number of ML MOOCs, and it made me wonder, like, what unique views do you bring to teaching and or learning machine learning and AI that you surfaced in the coursework, as well as which of the are there any views you have that you think kind of go against the grain of the way other people are approaching it?
Yeah, so I'm glad you enjoyed the classes. Michael and I had a ball, just a total blast doing it. And if you haven't, you should watch the Michael Jackson parody video we did about machine learning. You get to see Michael dressed up as Michael Jackson and dancing, which is well worth the price of admission, which is free. So you talk about this kind of interaction we had. One of the things that Michael and I tried to do is we decided that we've been wanting to do things together for a long time, but he's on one part of the country, I'm in another part of the country. We wanted to do this machine learning MOOC, and this gave us the opportunity to do it. And the way we decided to come at it's much like we're doing this now. We said, you know what, education like this should be more like a podcast. You should have a conversation. So every time we did one of these lectures, one of us would be the professor who would try to present the material, and the other person would try to be the student. So the professor would do all the preparation and come up with the sort of lesson and get everything together, and the student would do no preparation at all and would come in cold. So, in that way, it's just like regular school. And
Right.
we would just talk. And of course, he's an expert, I'm an expert, and this is what we do all day. So it's not like we didn't really kind of understand what was going on. But it turned out, and I think this really does come out in the conversations that we had, that we actually have very different views of what's important. Right. So Michael is much more of a theoretician. If you asked him what AI and machine learning is, he might say something like computational statistics. I'm much more interested in thinking about it in its kind of practical applications and, sort of what you can do as a practitioner to use these tools to make them work and to get synthesis. I want people to see that this thing over here is just like that thing over there, which is just like this thing over there, and they're all tied together. And I'm much less interested in proving in the abstract what it is that you actually can learn and what you actually can't learn. It's not that these things aren't important. I'm just less interested in them than Michael is. And so we would spend all of these times kind of arguing, sometimes obviously, sometimes not, about what's going on. And what I hope came out of that, and you can tell me if you think it's true or not, is that the student was drawn into this conversation and at least got the feeling that not only were they learning some equation or getting ready for some test or doing some assignment, but that there really is a deep conversation going on about AI and machine learning, and there's lots of different ways to think about it. And really that kind of gets to my larger philosophy about the way education works and why I'm so excited about the online education that we've been able to do. To me, what's really missing in education is access.
Right.
The ability for people to participate in the commons that is education, that is research, that is learning. And one thing that I think is important for people to understand is that when you say access, some people turn that into affordability. Is it cheap enough? Tuition's too high, and that is a part of access, but access is actually very different. Access is just the ability to be able to participate in the conversation, and that if you're capable of getting through it, being able to have the real opportunity to get through it. Affordability is only a small part of that. So one of the things that we've been doing, and I'm actually quite proud of this, over the last 3 years, is we decided that we wanted to push on this idea of access and affordability, and that online education and MOOCs were one way of doing it. And while we were working on this machine learning class, we wanted to make it a part of something bigger. And so Georgia Tech, when I was there in my senior associate dean role, I guess I still am, and in my professor role, we wanted to build an entire degree, a graduate level degree that anyone who could get access to the internet and then who had the time and had the desire would be able to get through an actual full-fledged course. A full-fledged, and not just a course, a full-fledged degree, a real program. And so we created this online MS program. It's exactly the same as our on-campus program. Same requirements, same degree. You get through this, you get a Master's of Science in Computer Science from a top 10 department, and it's indistinguishable from the one that you get on campus. And here's the thing that we did two things to sort of push on this notion of access. One is we decided to make it as inexpensive as possible. So the cost of the entire degree is something around $6,600.
Wow.
Depending upon how fast you get through the program. So somewhere between $6,000 and $8,000, sort of depending upon what you do, you can get an entire degree. That's pretty inexpensive. If you came on campus and you were an out-of-state student, it would cost you more like $46,000. Yeah. So that was the first thing that we did, make it affordable. But the other thing that we decided to do is we decided to admit every single student we believed who could succeed. This is a pretty big deal, right? If we think about our on-campus degree, we accept about 10% of our applicants. Mm-hmm. Why do we accept 10% of our applicants? Because it's all the space we have.
Right.
I'd estimate somewhere between 60 and 70% of the students who apply to our graduate program are above bar. But we've only got room for 10% of them, so only 10% of them get in. And by the way, it's basically a lottery, right? Mm-hmm. I mean, when you're a place like Stanford and you're accepting 4 or 5% of the people coming into your undergraduate program, there's no way that 4 or 5% really better than the next 4 or 5%, the 4 or 5% after that. You're almost closing your eyes and just picking people, right? Yeah. And this is what we were doing at the graduate level. We don't like that. For our online degree, which again is the same degree as our on-campus degree, at this point we're accepting about 60% of applicants.
Okay.
We have gone from 0 students 3 years ago to 4,000 students this term.
4,000 currently enrolled students, or is that a cumulative?
4,000 currently enrolled students.
Okay. Wow. And
that's pretty good.
To how many on campus?
About 200 or 300.
Okay.
In
That's
fact,
incredible.
by the way, it's not just that we've got 4,000 students. They're performing as well as the on-campus students. Oh, by the way, it's not just that we have 4,000 students who are performing as well as the on-campus students. They look very different. So if you look at our on-campus degree, about 85% of the applicants are foreign nationals, vast majority of whom are from India, following behind China. So about 15% are U.S. citizens. For our online degree, it's the complement. About 80 to 85% of the applicants are U.S. citizens or permanent residents.
Okay.
Right. They're in their early 30s, early and mid 30s, not in their early or mid 20s. Most of them are working full time. They've got, jobs mostly in IT, though not all of them. They've got mortgages, they've got kids, and they're trying to sort of get through their day, but they can't take the time to get further education or to do the thing they want to do because, again, they've got mortgages and kids and they've got responsibilities, right? So what's interesting is we've done studies of this. We partnered with Harvard and looked at it. We think that of the people who are coming through our program, almost none of them would have pursued an advanced degree otherwise. Because they just simply didn't have the option. They couldn't take 2 years off from their lives to go and pursue a degree because they had too many other responsibilities and things that they had to do. But this gives them the option of doing that. And so, in fact, the overlap between them and the people who normally would get educations is almost zero. Current estimate is that we'll add between 8 and 10% every year to the number of graduate IT workers in the United States than we otherwise would have seen.
And have you looked at what they're doing afterwards? How long has the program been in place? And how long have you been tracking that, and to what degree?
So it's been about 3 years. In fact, I think we're just ending our third year now.
Okay.
We'll be starting our fourth year. So people have just begun to graduate. We had 20 people graduate 2 terms ago. And this semester, we're expecting to see closer to about 250, and we're expecting to see a steady state of closer to 1,000 people graduating a year. Most of them already had jobs. So usually the way you measure success, you say, okay, did people get jobs when they graduated? Well, most of these people already had jobs. So they didn't lose their jobs. I guess that's a good thing, but it's hard to know what that impact is because the usual measures don't really make sense. But they all seem to be happy. 97% of them said that they would, recommend this to other people. Many of them do get jobs while they're in the middle of the program. A lot of them get promotions and they move through. So you'll have to ask me in 5 years what the real impact is. But right now it appears that people are happy. They're getting a lot out of it. Some of them are able to change careers, get promotions, and to do things they wouldn't otherwise be able to do because they just couldn't take the time off to do it. So I'm very happy with that and happy with the sort of impact it appears to be having on students.
Let me ask you this. A lot of people who listen to the podcast are, somewhere along the progression of learning and entering machine learning as a field, as a profession. And I'm wondering what do you think the right set of educational tools to take advantage of, right? MOOCs are a piece of that. But there's obviously other pieces that go into making a full, kind of a well-rounded student of machine learning and AI. How do you recommend that students approach that? Or do you have a philosophy around that?
Well, so I sort of do, and I do think it comes out in my class. If you actually take the class as opposed to watch the lectures, you get my assignments. And I'll just describe my first assignment to you because I think it actually captures a lot of at least what I believe matters in becoming either a machine learning researcher or a machine learning practitioner, or even AI, or more broadly speaking. So here's my first assignment. The first assignment is go find 2 data sets. I don't care what they are, so long as they're interesting. They have to be interesting by themselves, and they have to be interesting together. And you have to convince me that they're interesting. Then I want you to implement these 5 or 6 algorithms. And when I say implement, I mean steal the code. I don't really care. You don't get any credit whatsoever for implementing and running the code. You can steal libraries, go get your favorite implementation of KNN or boosting from somewhere else. I don't really care. And I want you to run all of those algorithms on those 2 data sets. And I want you to do analysis and explain to me why you got the behavior that you did. Why did some of those algorithms, which should all work, why did some of them behave better on one of the data sets than the other? What sort of things did you learn by applying those algorithms and doing the data analysis? Convince me that you've thought about it. convince me of what experiments you would need to run in order to really get the answers to the questions, and then run those experiments. Do all of that, and then write it up in 12 pages. Not 13 pages, not 14 pages, 12 pages. Why do I have an assignment like that? I have an assignment like that because I think much about machine learning, much about the field that we're in, is really about the practice of doing it. Theoretically, all of these algorithms, particularly in supervised learning, they're all very similar. They all can learn the same kinds of things, but there's no free lunch, right? So there has to be built into what you're doing deep assumptions about your data, what it is you're trying to accomplish, and you have to be able to surface those things. So if somebody asked me if I wanted to really do machine learning, what do I need to learn? I give them two answers. One, you need to learn the foundations and the fundamentals. Yes, you need to know the math. You need to understand information theory. You need to understand, what linear algebra is. You need to not flinch if somebody mentions an eigenvector or an eigenproblem to you. You need to get the math, yes, and you need to get the computing because it's a fundamentally computing-based discipline, and computing is not math. Computing is not engineering. Computing is not science. You need to internalize the computing part of machine learning. But just as important, and in many ways more important, I believe, is you have to really dive deeply into the empirical side of it. You have to get dirty with data. You have to understand what the difficulties are in answering the questions you want to answer. And you have to really realize that the questions you're asking aren't necessarily the right ones. Most of what traps us in machine learning and in lots of other things we do are the unspoken assumptions. And you have to surface what those things are. And I think that the best way of doing that is by getting your hands and your feet dirty. So my classes are designed to do that, to force you to get into a messy, ill-defined situation and to work your way out of it. So if you want to do data analysis, if you want to do machine learning, that's great. It's wonderful. I can think of nothing more interesting to do. But you have to get out of the textbooks. You have to play through the data and understand why it works the way that it does, why the algorithms have the effect that they do, why you can learn some things you can't seem to learn other things. And that, I think, is actually really missing. I think people either dive down the empirical side and just try to get stuff working, but with no understanding of the fundamentals, so they don't even know how to ask the questions. Or they get so caught up in the fundamentals, they don't worry about whether it actually works in practice or how you would actually apply your ideas. And you have to do both, especially in a field like machine learning.
Mm-hmm.
They use all the social media tools that are out there to build community, to talk to each other, to talk to the faculty, to talk to advisors. They really build an entire community around what they're doing. And really, the people who are in that community do well. And the people who are not a part of that community do poorly. So one of the things that's important about the trips that I've been taking and the traveling around the world I've been doing is making certain that we provide the tools so that people can build local community that makes sense to them, because that's how the learning happens. At least that's what I believe.
You guys might be single-handedly propping up Google+.
I'm about helping Google+. I think people haven't been nice enough to Google+.
I've never heard of anyone else saying they're using it.
Well, there's no lag because no one else is using it, so you got that.
Oh, nice. So let's switch gears a little bit and talk about your research. Your research, is your research focus, as I understand it anyways, primarily around reinforcement learning? Or maybe you tell us what your research focus is nowadays and how you think of that area.
Yeah, so like I said earlier, I really have been into AI and machine learning for a very long time. And it took me a while to figure out what it was about it that I really cared about. It was easier to see when I was reflecting back on it, what it is that, I found interesting, what I didn't. The kind of machine learning that I care about, the name that we kind of give it in the field is interactive machine learning or interactive AI. I sometimes refer to it as interactive AI because I care about the AI problem as much as I do the machine learning problem. And what it really is about what happens when you, instead of just saying, oh, look, here's some data, and I'm going to look at that data, and then I'm going to build a function, and now I can do some prediction. You know that you're going to have a fundamentally incremental and interactive process. So I want to model human beings, because I actually care about messy data, and there's nothing messier than people. So I want human beings to be a part of the story of how I learn. And when I say that I think that people learn only through social communities, or they learn best through social communities, I think that's actually true for our machines as well. So that ends up looking a lot like, and I spend most of my time worrying about reinforcement learning, so you're right about that. And the reason I care about reinforcement learning is that reinforcement learning is really, I think, trying to do something big and hairy, which is actually model what it means to be an autonomous agent. So when people ask me for the one sentence description of what it is that I do, I say I care about interactive machine learning. I care about building intelligent agents that have to interact with other intelligent agents, perhaps hundreds of thousands of them at a time. And some of those intelligent agents might be human. They don't all have to be human, but some of them will be. And since some of them are human, you can't just go around sending XML packets back and forth. You have to actually engage in conversation. You have to worry about the fact that human beings change over time. They're inconsistent. They're error prone. They're highly non-Markovian. There's all kinds of interesting things about people. And you need to be partners with people, and you need to be long-lived in order for you to make progress in the area. So that's what I really care about. I care about building a system that doesn't just predict whether, a car is going to run into the side of the road or not, but actually deals with the fact that there are several million other people on the road at the same time, and you have to interact with those other people, and you have to learn by talking to them and interacting with them.
And so reinforcement learning is a subset of that.
Yes,
right? And
that's right. I spend a lot of my time worrying about game theory. I spend a lot of my time worrying about marketing, believe it or not, about social behavior and how people tend to interact and work with one another, and how you can convince them to work with you, or how you can deal with them if they're trying to work against you. So it's the whole gamut of what it means to interact with other intelligent beings that have their own set of goals and interests that might not be the same as yours.
So tell me, you mentioned marketing. Tell me more about how that plays into your research, or maybe even give us an example of some of the research topics you've been looking into recently.
So I like the marketing question. So I spent a lot of time with a friend of mine, with one of my students who's now a professor in North Carolina, on something called drama management. So the short version of drama management is, you've played video games, right?
Yep.
And, the thing about video games is the interesting ones are ones where you're, involved in an entire world and an entire story. So what's actually going on is that the person building the system for you is trying to build a story. Mm-hmm. But most stories you just read and you're a passive participant of. And things like games, you're actually an active participant, which means there's this trade-off between your sense of autonomy and agency on the one hand, and me making certain that you have a good experience or a good story. So you can actually think of lots and lots of things like this. You could think about conversations that you have in interviews and a podcast is like a story where you're negotiating back and forth and trying to figure out how to tell the story that you want to tell, while still allowing people to say the things that they need to say or that they want to say. You can think about all kinds of examples like that. Could kind of go on for a while. But the thing there is that it turns out that because your player or the person who's participating in building the story with you has their own ideas, they might take your ideas off track. They might turn your murder mystery into a horror story. They might turn your interview, where you're supposed to be going back and forth and having a conversation, into a series of you ask me a questions and I say yes or no. And it's not much of an interview for you, right? So you have to influence what the player is doing, what the human participant is doing, or otherwise you don't end up with the good story that you want to have. So there are two ways of doing that. One, and I think you and most of your listeners, have you ever heard the expression a game that's on rails?
Sure.
So, that's where, well, I'm sorry, I'm just not going to let you go through this door, because if you do, it breaks the video game, right, or it breaks the story. Right. And so you're on rails. And the thing about being on rails is it takes you out of the story. Takes you out of the experience. And that's what a lot of people do. And a lot of the drama management stuff is about that as well. But there's another way of doing it. And in fact, the right way of doing it, if you can make it work, is you get the other person, the person you're interacting with, you're trying to learn with, the story you're trying to get to participate in the story, to actually accept your goals as his or her own. And it turns out marketing is very good at this. So we built this kind of system where you get people to do the things that you want them to do by putting them in situations where it's just natural for them to do those things. So rather than lock every door except one door in a room so you go through it, I make something happen, maybe some noise or something interesting that makes you want to go through that door. Right. So on the marketing, like
themes of behavioral economics and incentives and things like that coming into play here, right?
Oh, that's exactly right. So in fact, the example of this that everyone's familiar with is one called scarcity. So that's where it turns out that people, if they believe that something is going away, they suddenly find it more valuable.
Right.
Right. So anybody with kids knows, certainly anyone with kids 10 years ago knows, that Disney has this habit of saying, oh, we're going to release on DVD Beauty and the Beast, and then we're never going to release it again. And so everybody buys it, right? Because it's about to go away. Or, I mean, Black Friday's like this, right? You're going to, every year at the day after Thanksgiving, you go to the store to buy a bunch of stuff. It doesn't make any sense whatsoever. They're not even things you want to have, but they're going away. You're going to get a price right now. It's on sale. And so people react to that. They can't help themselves. And so scarcity is just one of the particular things. It's very easy to understand. There's tons of others of these. There's something called liking, which is, it turns out people will do things for you if they like you. People react to authority. Actually, my favorite example is something called consistency, where if you can get someone to say something out loud that they believe something, they have an almost pathological need to be consistent with it over time. Sure. So, do you have anybody in your neighborhood who won't mow their lawn? Here's the way you get them to mow the lawn. You wait till it's winter. Right. And so all the grass is, kind of dead and it's all the same height. And you start up a conversation and you say, man, it really looks great around here when it's like this. Everything's the same color. Everything's the same height. And if you get the person to agree with that, yeah, it looks really nice when it's like this. The next summer, they'll mow the lawn because they basically believe that's the way it's supposed to be. And you know what's really nice about it? It's not that you got them to mow the lawn. It's that they believe that they are in complete control of that idea, that they're the one who made the decision or are in charge. So that's a long story, but the short version is we built systems like this that basically convinced people to do the things that we wanted them to do. We influenced them. So I'm not using machine learning just to predict your behavior. I'm using machine learning to figure out how to intervene to get you to do something. And what I really want to happen is for you to believe it's your own idea. So we built this little story, just a quick example. We built this little story where the whole goal was to get you to buy a fish at a market. Not the most exciting story in the world. And there are lots of ways we can influence you to do this with scarcity and various other things. And so we had people play this game. And the people we tried to influence were much more likely than the people we didn't in buying the fish and doing the things that we tried to get done.
Sure.
Now that's interesting. But what's more interesting is that when you ask the people whether they felt manipulated or not, the people who were not manipulated were much more likely to say they felt they were being manipulated than the people who actually were manipulated.
That's interesting. Why is that?
Because the whole way this works, the whole way the kind of psychology works, is you feel as if you have agency, that you're making the decision. When something goes on sale and you decide you're going to buy it, you don't feel that you've been tricked into buying it. You made the decision to do it, right? And so what's really interesting, and this is why it's not just running the data and doing machine learning, it's actually understanding about human behavior. It's understanding behavioral economics. It's understanding the way marketing tricks work. It's all about getting the person to make the decision, themselves, that they want to do this thing, and then they have agency, they have control, and they're much more likely to see it through. The fact that you kind of trick them into doing it is neither here nor there.
So a quick note for listeners, anyone that's interested in digging deeper into some of these ideas, there's a great book called Influence by Robert Cialdini that is super accessible and covers all the things that you talked about, consistency and scarcity, things like that. Mm-hmm. But this brings up a question for me, and that is a lot of the work we read about reinforcement learning nowadays is you're training these agents to navigate a world. Right. And then the work you're describing is you've got this world that's essentially training the human to navigate it. And there's an interesting complementariness to it. And I'm wondering if that complementariness has been explored at all. Like the things that I'm thinking around are like adversarial networks. Like, can you have the one training the other, thinking it's training the other? Does that make any sense? Is anything happening there?
Oh yeah, that's actually a very common way of doing it. So the thing that really got me into reinforcement learning when I was a young graduate student a couple hundred years ago was actually playing games. So there was this guy named Tesaro who had built something called TD Gammon, which was a particular way of doing reinforcement learning to learn how to play backgammon. And the way it learned to play backgammon was through self-play. So it played both sides of the game, and it learned by playing itself how to get better. And this is I think a pretty well understood sort of technique for learning, right? Sure. It's difficult to if it's too hard, you can't learn. If it's too easy, you can't learn. You need it to be just about a little beyond your current level of understanding. And so, yeah, this kind of thing happens all the time. Now, it is true that a lot of people who worry about machine learning do not think about the kind of complementary nature, that rather than there being an agent that's training in an environment, the environment could be, in fact, training the agent. And people don't always see that. In fact, my biggest complaint, or complaint's not the right word, but my biggest I don't know. Let's say complaint. My biggest complaint about the way machine learning is portrayed is that it's portrayed as a supervised learning problem. I'm going to give you a bunch of input-output examples, and you're going to learn the function that maps input to output. And that's interesting, but I think reinforcement learning is more interesting because it's this bigger problem. You don't have inputs and outputs. All you've got is actions you can take and feedback you get from the world, and then from that you have to figure out how to behave. That feels richer to me, even though in some sense they're equivalent. The unsupervised learning is a very different way of thinking about the world, even though, again, sort of mathematically they're all kind of equivalent. And that kind of breadth of what machine learning and AI is something that I don't think we spend enough time really thinking about. I think people tend to focus on the supervised learning part instead of the reinforcement learning and the unsupervised learning part, at least in the kind of popular press.
Okay. So maybe taking a step back, how do you think about the current state of reinforcement learning? Like, can you characterize the major research efforts, or even is it possible to characterize the major research efforts into a handful of directions and kind of who's doing what?
So I think there's so the answer is no, it's way too broad, but there's a couple of things that I think are really interesting. One is all this work on deep networks and deep neural networks, which is the current thing that everybody's really into. And by the way, it's really good work. I know the people who've been pushing on that for years and years and years, and they've really been able to do a lot of interesting things. They got the kind of fundamentals right with the math, and they're taking advantage of the fact that we have insane amounts of data so that we can actually sort of take advantage of those algorithms and do cool things. A lot of what's going on, at least in my world, that people are paying a lot of attention to is figuring out how to use the stuff that we know from deep networks and from deep learning and applying it to reinforcement learning.
Okay.
And rather than doing the supervised learning take where you said, well, okay, here's the state of the world, tell me what to do, you're actually treating it the way you treat a reinforcement learning problem. You're talking about building value functions over what the states are in the world and what things are better, and then using that to figure out how to make a decision and use what you learn from making the decision to affect your view of what's valuable in the world, and kind of having each one feed into one another. And so recognizing that there's at least two parts of that problem instead of one part of that problem is a really big deal. And being able to marry the kind of math that's come out of supervised learning has been, I think, really important. That I think has been really interesting. Has pushed forward a lot of what we've been able to learn in the last couple of years for sure. The second thing, which I think is interesting in part because it's my own work and places where I lived, is very related to what we just got through talking about, and it's this interactive machine learning. It turns out, I mentioned earlier that there's no free lunch, right? So for those of you who don't know, the no free lunch theorem basically just says that all algorithms are equally good. And in fact, not only are all algorithms equally good, but none of them are any better than behaving randomly. And the reason that's true is because over all the infinite number of problems that one could encounter, any algorithm has just as good a chance of doing well as that as any other algorithm. But it turns out in practice, we don't care about every possible problem in the universe. We care about a small set of problems in the universe. And what allows us to get leverage over that small set are built-in assumptions about that world. So the problem of learning is difficult and in some ways impossible, but it turns out people are really good at solving the problems that people are really good at. What they're really bad about is explaining to you how they do what they do, but they're really good at solving these problems. So a lot of what's been going on in the reinforcement learning world in particular is taking advantage of people. Learning from getting people to tell you something or to demonstrate something to you about how to do something so that you can learn much, much faster than you ever would. And really what you're getting out of it is you're getting the human beings' assumptions about the way the world works, and you're taking advantage of those assumptions to narrow down the search space. So I'll give you a really quick example. So it turns out that people do not think about things in atomic actions. They tend to think about them in these big, temporally extended views of the world. So like take something like Pac-Man, right? If I asked you to explain Pac-Man to me, you wouldn't be describing in terms of up, down, left, right, or what. You would say things like, oh, well, look, you need to get the power pellet. You need to avoid the ghosts. You need to, you need to do these 4 or 5 things. And we run experiments on this where we ask people to create buttons that they would use to make Pac-Man go faster, and they come up with these interesting buttons, these sort of long-term things. But dividing the world up like that, not from up, down, left, right, but into get the power pellet, avoid the ghost, is something that is very difficult to learn from scratch. But people have already figured this out. So you build systems where people are able to express to you those tricks, those shortcuts, those assumptions about the world, and then you can learn so much faster than you would ever be able to do on your own. And that's kind of where we're getting a lot. Basically, taking assumptions from the world and getting them automatically from humans. I think that's incredibly important. And one of the reasons I think it's important, by the way, is because so many of the problems that we actually care about involve people, right? They involve other people. They involve interacting with people. And so you have to understand the fundamental assumptions that people are living in, and you have to take advantage of them if you're ever going to learn. So those are 2 areas that I happen to think are really cool in the reinforcement learning space right now.
Are we also learning how to enable the machines to make the assumptions themselves? Like what's happening there?
Yeah, but the way they do it is they kind of do it. They do it by dint of observing the world, right? Michael Littman always says a couple of things that I really like, and one is that, if the person who's doing the programming is doing all of the learning and writing down the data structures, then you're stuck, right? You need the machine itself to be able to learn its own data structures through observation. It needs to be able to build its own assumptions and its own models. If you're always giving it the model, then it's always depending upon you to give it the model. It has to be able to build its own model. So fundamental to that is this idea that you're going to learn these. You're going to build in your own assumptions. You're going to learn new assumptions, and you're going to build models that you're willing to adapt. And so yes, that's definitely built into it. It's definitely a part of what's going on. But the problem is, absent nothing, or absent anything, you can't know where to start. And so this gets us back full circle to this idea that learning is a social exercise, right? As human beings, we interact with other human beings that have a bunch of assumptions. They built the world together, and they kind of know how it works. And a lot of your job is to figure out what it is they've built into the world as assumptions so that you can begin to learn. And our machines have to be able to do the same thing, or otherwise they're not actually living in the same world that we're living in.
Interesting. One of the papers that I pulled up of yours on Archive is paper Perceptual Reward Functions, which is pretty recently published. And that goes into, I think, the former of these 2 areas that you mentioned, where you're trying to map kind of the deep learning to, a broader set of problems. Can you describe that, the paper?
That is relatively new stuff. There's a bunch of new things that are coming out about that. A student of mine, Ashley Edwards, is really buying into this. The fundamental idea there is that people have people's reward function. So if you're a machine learning guy, right, particularly reinforcement learning guy, you start talking about rewards and you start talking about states, and you divide the world up into the abstract space, and you go, that's how you solve problems. But we spend most of our time never actually worrying about where these things come from. They're just given to us. And this paper is a part of actually a larger body of work that I've been paying a little bit of attention to the last couple of years, of trying to figure out where those things come from. Are there principles about where reward functions come from? Are there principles about where state comes from, at least with respect to the way human beings deal with it, so that you can actually solve these problems in general and be more robust to small changes in the environment? One of the things that's true about reinforcement learning is, there's a nice little math equation that you need in order to figure out how to learn and determine value. And it's very nice and it's very elegant, but it's actually quite fragile. So if I were to build a system, let's say a robot, and I wanted this robot to get from one end of a hallway to another, and along the way it might do some other interesting things, I can construct all my little alphas and my learning rates, and I can put everything together so that eventually it will learn and that it will do exactly what you want it to do, and it won't get so scared that something bad will happen that it won't move, and it won't get so distracted by some interesting thing over here to the left that it'll never get to the end of the hallway. I can actually do that pretty well. But then if I take that robot and all that it's learned, and then I make the hallway 5 inches longer, it will stop working, right? Because the math is very brittle. Everything is set up just right so that everything kind of touches one another. And what you want to do is you want to build systems that are robust to that. You want to build systems that adapt to that. And it turns out that human beings are very good, in fact, optimized in some ways for dealing with, it's still a niche environment, right? We do pretty well on Earth. We won't do pretty well on Mars, right? We don't do pretty well in space. but it's still a rich environment that we're in, and you want to build systems that can do that. And so the perceptual reinforcement learning stuff is about using what we get from our perceptions directly as the notion of state and as our notion of reward, that we try to get things to look like what we see. We try to imitate the things that we see through our perceptions rather than build simple or actually complex optimization functions that tell us whether this thing actually is like that thing. No, you just think about what it is that you see, what it is you're perceiving. And there's this sort of larger philosophy around that. I'm actually quite excited about the work. I think what it allows us to do is to stop thinking about reinforcement learning as a 5 tuple where you have to set the values, and start thinking about it as a larger programming problem, where the whole thing is reinforcement learning is not the thing that you start with. It's the mechanism by which you happen to solve the problem. It is itself a programming language. It is itself a way of viewing the world. And you've got to step back to the level of task and problem instead of thinking about solving this particular equation.
Interesting. Yeah, I thought the example that was provided in the introduction to the paper was a good one. That was training a robot to fold origami. Like what's the state of an origami, and how would you represent that traditionally? Whereas what's natural for us as humans is to see a picture of the final result, and how do you define a score metric or a distance metric from, a given current origami to this target?
Yeah, it's a rich problem too, because if I ask you to explain to me how to do origami, which by the way I have absolutely no idea how to do, something magic with your hands, paper, you do a flurry of things and then suddenly there's a dragon. I really don't know how it happens. But you start saying, oh well, you start thinking about folding it, and you start talking at this very high level, just like with Pac-Man. Right. And the way of dividing up that world is actually important, because if you don't divide up the world in the right way, you will never in a billion years, in the lifetime of the universe, actually solve the problem, because there's just too many possibilities. Right. This goes all the way back to language learning. And, it turns out that people do not actually correct their children. Right. So you don't get any negative examples hardly at all when you're a kid. And yet somehow children learn to speak their particular language. Right. Even though nobody's telling them when you think you are, but you don't actually correct your children. And we can prove to you mathematically that you can't learn under those circumstances. So the only way it can be happening is if the world has been divided up into nice little ways, and there's only a few possibilities, and you're searching over those few possibilities because the world's already been divided up for you. If you have to go through the trouble of dividing up the world yourself, then there isn't enough time. There aren't enough examples. There isn't enough time.
Yeah. So now go ahead.
No, I was just going to say, so to me, if you pop up to the AI level instead of the machine learning level, right, that's really the interesting thing, right? What's really exciting about AI right now, what's really exciting about machine learning right now, is that we finally have enough computing power, we finally have enough mathematical sophistication, and we finally have enough data that we can actually start solving really hard problems where we're going to be forced to move beyond, the equation that we wrote down in 1965 that hasn't changed, to thinking about bringing in all of these other things, whether it's marketing and behavioral economics, whether it's game theory, whether it's, engineering, whether it's control. We're actually going to have to bring in tons of other things in order to solve the problems. We're now at the point where we can actually do that. So we're actually meeting in the middle. So this is why this is an exciting time for me.
Nice. So at the risk of asking a question that we've kind of touched on in a couple of different ways already, for someone who wants to dig deeper into the kind of stuff we were just talking about, interactive machine learning and AI and reinforcement learning, are there any places that you would point them to get started?
Well, I would start with just a basic machine learning class, particularly one that covers reinforcement learning. If you really are interested in reinforcement learning as a topic, Rich Sutton's book is freely available online. It's a great place to start to kind of understand what's going on. The class that I teach with Michael Littman is freely online. There's lots and lots of examples out there. I would actually start with that and get the basics. There's survey papers. I mean, Google is your friend in this case. Sure. But if you're the kind of person who wants to have someone give you a nice brief overview of what's going on, then hey, start with my class. Just pick Michael Littman. You can go to Udacity. You can get it for free. Just sort of skim through it and watch through it, and you'll figure out from there where to go. And I would really encourage people to pick a problem that they find interesting. If games are the things for you, then start looking up the deep reinforcement learning work on games. There's a bunch of work done recently on solving most of the Atari games using deep learning. That's really interesting stuff. The problem with starting there, though, is that now you have to know what convolution nets are, and you're going to find yourself distracted for 9 months while you learn enough math to figure out what's going on. I would actually start top down. I would start thinking about the problems, what the issues are, before I get so deep into the math that I get lost. You don't want to lose the forest for the trees here, and it is very easy to lose the forest for the trees because there's so much kind of interesting and very difficult math that's underneath all of this. But really, you want to keep sight of the goal, right, which is to build something that can learn over time, can adapt over years, can live for 20 years and continually learn and adapt. And think about what that would mean. Think about what it would mean to you as a person, and then start asking what kind of background you would need to have in order to build a system that does that.
That's great. And I'll include links to a bunch of the things that you mentioned in the show notes. I think.
Let me add one thing to something
thing.
You should throw in the show notes. You mentioned the book Influence. I would also recommend The Media Equation.
The Media Equation.
That is a fantastic book. It's one of these. It's a short book about how human beings actually behave, and how it turns out that people will treat machines as if they're humans, even though they know better. Because they'll treat anything that acts like it has intention as if it has intention. And I think that fact alone should influence everyone who's thinking about building systems that have to interact with humans.
Interesting. We're not even all that good at ascribing intention to other people. The thought of applying it to machines is, and we're going to have to work on that.
I actually think it's the other way around. I think the problem is we're incredibly good at ascribing intentions to other people. It's just not always the right intentions.
Yeah. Great. So I think this has been a great discussion. I appreciate you getting together with me for it, especially on a Saturday morning, and don't want to monopolize your Saturday. So we'll wrap things up here. Anything else you'd like to toss out?
No, just I really enjoyed this, and we should have this conversation again.
Absolutely. And then for folks that want to get in touch with you, how do they find you on Google Plus?
Well, if you go to Google Plus, I'm the one guy who's still there. So that's pretty easy to find me. No, just send me an email. It may take me a while to respond, but I'm more than happy to respond. Just Google Isbell at cc.tech.edu.
Okay. And are you on Twitter or any of the lesser used social networks?
I have a Twitter account, and occasionally I even use it. But really, email is the only way to really get to me, unless you have my cell number, and I'm not giving you my cell number.
Nice. All right, great. Well, thanks so much, Charles. Really appreciate it. And next time.
Absolutely.
Awesome. All right, everyone. That's our show for today. Thanks so much for listening. If you're one of our lucky winners or runners-up, please reach out to me at sam@twimlai.com. A bunch of you have asked, hey, what's up with the newsletter? No, you haven't missed anything. I've just been crazy busy and haven't had a chance to get one out. I'm so sorry about that. I'm still working on it, and I'll keep you posted. Thank you so much for your support, and catch you next time.